All right. Good afternoon, everyone. I think we're going to get started on the second session. Um, this session is navigating AI and machine learning, considerations, applications, approach, and scale in order to get your desired outcome. Today we have Ian Hamilton and Michael Spear from VHP.
Good afternoon, everybody. Appreciate y'all joining us for this introduction to AI machine learning. We're covering several of the similar topics to the presentation before us, but I think with a little bit more of a diving into the AI and machine learning side of things. So if this is old news, then I can definitely talk about projects. That'd be equally as fun. But the main reason we want to talk to you today is to make AI and machine learning more clear and more tangible. These are not black boxes. These are things that you are able to work with yourself if you're so inclined. And if you are someone who either works with team members who work with AI or people who would do the types of analyses that would do machine learning, help you understand sort of what are you asking for, what's their process, how are you able to sort of help them work with you if your part of the work is not necessarily AI or machine learning related. So what do we mean by artificial intelligence and machine learning? So the last presentation, I think, did a good job of summarizing overall. But basically, it's a whole set of nested concepts where AI is this much bigger field of study that covers a whole range of topics. And then within artificial intelligence, we have things like machine learning. We've got neural networks. We've got deep learning. Obviously, I'm sure everybody here is familiar with ChatGPT or large language models. That would be a subset of artificial intelligence and a subset of machine learning. Within all these methods, so within this great big circle of potential methods that fall into the scope of artificial intelligence, machine learning, there's sort of this tension between interpretability and performance. And so when someone is talking about different types of methods, you're considering this trade-off between, do I know what the machine is thinking versus how insightful is the model going to be, or how nuanced is the model? So at this far end here, where we've got high interpretability, we've got linear regression, which you might be familiar with. That's basically just a very simple math equation. That is A times B plus C times D. Very easy to interpret what's going on, but it's not very nuanced. And so as we sort of go down this graph here towards the more performance-oriented side of things, we get neural networks, which are really great at doing high performance calculations, looking for insights and deriving differences between data sets very efficiently and very fast. But sometimes it's difficult to interpret what is the machine thinking? How are we actually making the distinction between these different data sets or different data points in the system? So we're going to walk through just a few things here to sort of help clarify some of these things. Talk about our example needs, talk about some potential pathways so that, if you're not the person who's doing the analysis, maybe you're working with the people who do the analysis, help understand sort of how their process is working or how your process or their process could potentially work. And then we'll sort of walk through some examples of doing a custom where you're not sort of taking an out-of-the-box tool. So a common use case of machine learning is computer vision. And what computer vision is essentially a way of feeding an algorithm imagery. It could be street view imagery, it could be aerial imagery, any imagery that sort of, you would pick up with any sort of camera or sensor. And you're feeding it to it and you're asking the computer to make a decision, what am I looking at? Either I'm classifying this image and saying what is in my image, or I'm picking out specific features, that latter part being a sidewalk. We'll cover two sort of very high-level examples. One was sort of classifying paved versus unpaved roads and doing sidewalk detection to sort of clarify, these two different types of approaches for computer vision in a standpoint. And I guess just to sort of clarify, I should have mentioned up top, my background is in transportation and safety in particular. And so focusing on the service type of the road and focusing on the presence of crosswalks or other types of facilities, very much in my wheelhouse. But if you're doing utility work like the last presentation, or you're doing another part of the sort of civil infrastructure, all of these approaches are very applicable to what you do. So what does the computer see? At a very core level, especially if you're asking it to make a classification assumption, you're essentially asking it, you're feeding it an image and you're saying, this is what counts. This is what I'm looking for. And so everything that you see like similar to this graphic, this image, I want you to say that is an unpaved road or that's a paved road. And then you would feed another image and say this is not that, this is something completely different. And you would feed these images to it to train that model to then test it and then deploy it on a much broader data set. So in this example, we've got a whole bunch of yeses and a whole bunch of nos. And this is based, I promise, based on some sort of rule that we've programmed the machine to say this is a yes, this is a no. And what happens when you feed it this? What are the rules that the machine is using to determine yes or no that it can then use to determine is this a yes or is this a no? Any guesses as to what the yeses and nos mean from the audience? Does anybody go for it? Good, good. You're halfway there. It changes. Any other guesses? No? It's okay, I didn't get it either. The number of angles, if it's an even number of angles, it's a yes, unless it's purple, and then you invert it. And so again, this is what the machine is seeing, right? So you're basically feeding it an image and saying, what is this? This is what I think this is. And so now it's asking to make that determination later. Based on what you've told me, based on what you fed me, I think it's this. So there's a few different ways in which the computer model, the machine learning model can work, especially if you're sort of feeding it imagery. Logit and support vector machines are two examples. And all it's really doing is it's taking the data that you fed it, say unpaved versus paved. I'm feeding it a bunch of images and say this is an unpaved road, this is a paved road. And then you feed it more images. And it's trying to group these images in certain ways based on certain characteristics to say, I'm pretty sure this grouping of images is paved and this grouping of images is unpaved. By Logit, you're sort of doing this probabilistic inference to say, clustering down here is more likely to be unpaved, whereas clustering up here is more likely to be paved. In SVMs, it sort of puts this on a 2-axis graph, or 3-axis, or however many axes you use, and draws a line across the image, across these data, and say, everything to this side of the line is paved, everything to this side of the line is unpaved. As the dots indicate, the model is not always perfect. I think that's a really important thing to understand, that the machine learning model, like any model, is not perfect. It cannot be perfect. In the same way that if we fed a human information, or the example that we gave in the previous slide, is liable to make mistakes or misinterpret what they are saying. So that gets us to a tangible example. One of these roads is paved, and one of these roads is unpaved. Which is which? Who thinks the hat of the T is paved? 4, 5 people. Okay, people are deciding. Okay, maybe a third of the room, half the room. So that if you think the stem of the T is paved, raise your hand. And some people are unsure. Which again, computer vision models, confidence is a big part of that. To be honest, I've forgotten as well. I'm pretty sure this is unpaved. So the unpaved road actually looks kind of a bit better. I think, in my mind, when I first saw this, I thought this was unpaved. Why did I think this was unpaved? It seemed like the edge looked a little rougher. It seemed like the surface might have been a little bit rougher. It seems like this is smoother. And so maybe that would have been paved. But my recollection of this was the one that I thought was paved is actually unpaved. And again, the fact that the room was divided on this, and I'm pretty sure not everybody raised their hand, just reflects that this is what the machine is seeing. Are we expecting the machine to be better than the typical human when we know what a paved and unpaved road is? And so again, that confidence comes into play. And this is a project that we did in Kansas. We've also done it in Oregon and a few other places for Federal Highway, where what we do is we do roadway classification to determine if it's paved or unpaved, both using an estimate for each individual image, but then also making a classification for the entire roadway. And so in the same way that we're asking, is this paved or this is unpaved, if we say that 2/3 of the roads in our study area are paved and 1/3 are unpaved, that means if we were to take a random guess, if we were to basically guess based on that information alone, 66% sure that any one given road is paved. If we feed it one image and say, is this road paved or is it unpaved? The machine model will guess, I'm 65% sure that this is paved. Therefore, I'm a little bit sure that this entire road is paved based on that one image. If we keep feeding it information, it now says, well, I'm 80% sure that that's paved. Therefore, I'm a little bit more sure that this road is paved overall. Then we feed it another one, and it thinks, actually, maybe this is unpaved. This kind of looks unpaved. Do it again. I still think it might be unpaved. And then it says, okay, now I'm seeing features that are more indicative of a paved road. I'm becoming more and more confident that this is a paved road. And this is just one example of how you can take individual processing in a machine learning algorithm to then make a classification for an entire roadway. Thinking back to that whole blue and angle example, what's the machine looking for? It's probably seeing things like edge lines. It's probably seeing things like center lines. It's probably seeing the darkness of the asphalt as an indicator of this is a paved road versus an unpaved road. As we get to these examples, that center line's kind of washed out, kind of blends in the background. The asphalt's lighter, it's more worn out. That means it looks a lot closer to an unpaved road than it would otherwise. When you get to sort of this 4-lane divided highway or 4-lane road, you see those lane lines again, you see more darker asphalt. All of a sudden, the model's more confident that this is a paved road. So that's kind of a very quick overview of, so what's the machine thinking when you're sort of feeding this information, how we're going about making these decisions. I'm going to very quickly run through some very high-level examples of just how you can sort of deploy some of these models in the real world. So there's a couple things you can do. First, the last presentation, you did a good job sort of covering some out-of-the-box tools that you can use to deploy some of these machine learning models. There are pre-trained models available for GeoAI, which is an Esri product, I believe, right? And these are very easy to use. So very out of the box, basically you can do a pixel classification, do feature extraction, just a lot of great information to sort of pull out from the beginning. And then if you're curious, here's some examples of some models that you can deploy that are pre-trained. And some of these will do sort of that feature extraction where you get these polygons based on the location, and then also the classification as well. Anything you'd want to add to the pre-trained models? No. And so let's say, are we doing on time, by the way? Are we doing okay? Okay, awesome. Want to know how much we need to devote to any of these one things. So why would you not want to use a pre-trained model? So pre-trained models are very good for just out of the box, deploying on your network. It seems like it's a really easy solution to deploy some of these more complex concepts. So they can be often plug and play, but there are several reasons why you would want to then tweak a model, or maybe, as Michael's going to get into, build your own custom model. So a couple of those reasons are a different imagery source. So if you're detecting imagery from a different sensor, either from the air versus the ground, or maybe you're using a different sensor, from an aerial source, those are often just sort of different pixelation, different resolutions, different features in them. And so there can be some confusion in the machine based on that difference of data that you're feeding it. The model may also not be trained to your geography. So a couple things, in that example, when we were doing this machine learning classification model for FHWA, there's a difference between the imagery in Oregon and the conditions in Oregon versus the conditions in Kansas. A lot more trees in Oregon, for one. And so those differences, those distinctions are just things that the machine is not aware of if you're training your entire model in Kansas and then asking it, how do I handle this coniferous forest in the Cascades? Just very different things for the model to be parsing if it's never seen that before. Another example is it just may not be trained on your assets. Is anybody here from California? No? Has anybody been to California? Okay, all right, awesome. That's fine. Trying to be relatable. One thing to do in California that's not typical across the country, in school zones, their crosswalks are yellow. And so if you're trying to do crosswalk extraction in a place that has different MUTC date standards or different type of assets, either color, shape, whatever it might be, if it's never seen a yellow crosswalk before, it's going to be way more uncertain that that's a crosswalk than if it was another type of similar sort of traditional white striped crosswalk. And so again, I'm sort of going through this very quickly because I think the custom side of things is pretty interesting. But I just want to point out that we've got this pre-trained model that can be deployed from GeoAI, and then there's these other tools that you can use to help sort of tweak it towards your specific needs or specific geography. Again, this could be a college course in of itself, so we're not going to go to it in too much detail. But I think, again, I just want to make sure that we're covering some of the high-level components here, that there are requirements, software packages, there are the images that you may want to pull in, and there are different tool sets, right? So when you're sort of discussing, are we going to do this in-house versus are we going to contract this out, these are the types of decisions that either your contractor or your colleague is making versus what you could be doing as well. And then, of course, what's your hardware? Is your GPU able to handle the processing power? How fast are you able to feed it images? These are the types of trade-offs. I want to get to the custom part pretty soon. So the one thing I'll just say is, as the last presentation also listed, as you go through this process, you do need to provide a training data set. So you do need to have images that are labeled. You are classifying and say, this image is a crosswalk, that image is not a crosswalk, this is a roundabout, that is not a roundabout. And so just making those sort of, considering what am I feeding this model to make it sort of applicable to my specific use case. And then finally, I do want to make the point, we're all GIS people, I assume. This is a pretty GIS-centric conference. So we're all familiar with the phrase garbage in, garbage out. If you are feeding the model a specific type of input, you're going to get that input. If it's not high quality, if it's got issues with it, if you've got a high level of shadow associated with things, or you don't have different use cases such as dark pavement versus light pavement, it's not going to be able to pick up on these things. And so as either you are developing your data set or you're working with someone to develop that data set, these are the types of trade-offs that you need to consider, even if you are deploying some of these pre-trained models that are out of the box and could be used. So with that, I'll hand it over to Michael to talk about developing a custom model using open source.
Cool. Thank you, Ian. Yeah, so sometimes some of those cool pre-trained models that Ian just mentioned may not be best suited for your needs or the types of objects that you're trying to detect or classify. And also, like Ian said, this is the sort of thing that you could probably take a whole college course on. So I'm going to kind of go over a pretty oversimplified example workflow of a specific use case for training your own custom machine learning model. And so for this example scenario here, I'm trying to inventory essentially high visibility, or what I like to call zebra crosswalks in North Carolina. And we have some examples on the screen here. And like Ian, I have a traffic safety background. And so having this sort of data can really help with certain safety analyses and decisions that we make. And so basically, where will I start? A lot of these algorithms are open source and available to the public. And so I decided to go with a model called YOLO, Y-O-L-O, which stands for You Only Look Once. And that is a computer vision object detection model that can extract objects from visual data like images or videos. And so I've broken this up into 4 main steps. So the first one is preparing your training data. It's really important to have quality training samples. And so you can see here are some training sample bounding boxes that I drew around some high-vis crosswalks in Raleigh. And I have a few tips up on the slide here for creating your training data that Ian alluded to earlier. So you should avoid training your model on the same imagery as the study area where you actually want to run your detection. And that is just to keep your model honest and make sure that your model is actually detecting things rather than regurgitating whatever it was trained on. And then also, if possible, not necessary, but use the same or as similar possible image resolution and file type for the best results between your training and your inference data. So once you've gathered your training data, now is time to train and validate your model. And this is probably the most important and time-consuming portion of this whole process. And so again, I'm not going to go too deep into it because I could probably talk for hours about this. But essentially, the machine will go through, or the machine learning model will go through all of your training sample data and learn what a high-vis crosswalk looks like. And these open source models have many, many different parameters that you can tweak to fine-tune and adjust your model. And so as you can see in the little flowchart I have down here, this becomes a bit of a recursive process where you continue to refine your model until you get rid of some of that noise like you see on the outsides of this image here, and you're only really detecting the things that you want to detect. The third step is preparing your inference data. The most important part about this, since we are at NCGIS, I'm going to add a spatial component here. And so I've extracted a GeoTIFF, which is a georeferenced image of, this is downtown Winston-Salem, so we're actually sitting right there in the middle of that map. And detecting images on a georeferenced image file will allow you to then convert that YOLO output to a GIS-enabled data set. So having that prepared inference data handy, you can now run your trained model to detect your high-vis crosswalks in downtown Winston-Salem. YOLO is, like I said, not an inherently spatial model, and so it'll output a text file of bounding box coordinates relative to the image's pixels. But what you can then do is perform a mathematical conversion between those pixel coordinates and the stored geographic coordinates in the GeoTIFF file to then create a spatial file like I have here, which is an Esri feature class or shapefile. And so if you're going to take anything away from what I've just described today, I really just want to drive home that these AI and machine learning tools are more accessible today than ever. You can train your own model, and this is feasible by using solely open source data as well as open source machine learning algorithms. And also, there's much broader applicability than the high-vis crosswalks that I train my model on. Just about any object that's visible in the imagery you can use to train your own object detection model. So with that, I'll hand it back over to Ian to close this out.
Appreciate that. So I think we've got about 3 minutes left, which is great. So we're just going to close it out here really quickly. First, just saying that this is usually only one input into an overall process. So if we're thinking, this sounds great, this is interesting, but how does this really affect me? I just want to see the big finale here. There's a lot of things you can do with the outputs from these models. And one thing we're actually doing with NCDOT, or did with NCDOT, is we worked with a machine learning vendor who typically does this stuff for insurance companies to extract pavement markings. And once you've got those pavement markings extracted, you can now determine things like turn lanes at intersections, or crosswalk presence at intersection, or bike lane presence at intersection. And from the safety side of things, that just means we can do much more deeper safety analysis and compare sites apples to apples based on some of that contextual information. So again, if this seems abstract, it can very easily be made much more tangible. I don't know, will these slides be shared after the conference? Or?
There would be a YouTube video.
Oh, fantastic, awesome. So I'm going to hold here mostly for the YouTube video so people can hit pause. But the idea is that there's a lot of considerations into sort of doing these models and pursuing this type of work. Again, if you're not the person who would be necessarily pushing the buttons yourself, hopefully these are kind of prompt questions you're asking yourself as your colleagues are working with these data, or if you're working with a vendor to make some of these decisions and determine if this use case is right for you. I see a photo back there, so I'll pause. But with that, we do really appreciate your time. The idea was just to make this less of a black box and hopefully sort of show you underneath the hood of how this is going to work. More than happy to answer any questions or talk about these models. Yeah, sure.
What imagery are you using? Is it mainly public data, or and then also what pixel resolution are you finding to be the best result?
That's a great question. So what I would say is, I sort of touched on it earlier, anytime that you develop a model, you should probably use the same imagery to then deploy that model, or the same input data. For projects like the Oregon classification, the FHWA service classification model, we're trying to use as much open source or publicly available imagery as possible. If you were to contract with a vendor to do some of this extraction, they often fly their own data and train their own models on their own data because their use case might be insurance claims or impervious surface or things like that. So it just depends. Are you someone who's sort of more of an end user, or is it your business to collect these data and process it? To the resolution part, I would say 1 foot is you must be that tall to ride. If you can get underneath 1 foot, the better. But I'd say any kind of use case we've seen with machine learning needs to be at least 1 foot. Yeah. Yeah.
So much. It's a great presentation.
Thank you.
Can you run a small clip of how algorithm work to create anything?
So could I run a small clip or what? Sorry.
Yeah, it's not a clip of videos, anything you have. So it would be more understandable to us.
Yeah, I guess that's a good question. Maybe if you want to give us your card afterwards, we can sort of show you how we do things. I don't have a clip handy right now, but I've got the sort of very, Bayes process there in the beginning is probably the best we got. But have you ever worked with Python before? You're doing it. The Python interface is often a way to work with that data. Yeah. Yeah, absolutely. I've never personally worked on a project that has done it with video, but it certainly can be done with video. This is more my 2 cents on things. The way that I would sort of run it would be hitting the stills and classifying it based on stills. People I've talked to who do work on videos, often the trick that they have is the position of the object in the video. Because there's going to be several frames where you're saying that sign is there, that sign is still there, that sign is still there. And so tracking so that sign is this point in the process is the trickiest part, although it is certainly a solved problem as there's plenty of vendors who will do things like that and do that extraction. Sure.
Is there an open data source for Street View imagery that you've been able to successfully use for machine learning projects?
Another great question. Open source. I know that Mapillary and Google Images, Google Street View, will let you hit it for a very nominal fee. One of the best applications that I've heard of, the Nevada DOT, since they know where their intersections are, they just want to know what the signal head is. They will say, from this point in the network, give me a snapshot of Google Street View. And so instead of processing every point along the Street View line and doing, 10 cents, 10 cents, 10 cents, 10 cents, it's, at each approach to the intersection, so it very much minimizes the cost of hitting some of those more proprietary data sets. You can always drive it yourself. That's the most open source, is if you drive it yourself. Yeah. Sure. That's it.